Hello everyone and welcome back to Schemanicus, and we're back again with another stream right here. And since I guess it's been only 2 days since the last stream, but many questions go unanswered. So that is the reason for this stream. And we'll again continue as usual. First, I'll wait for some people in here. As in, hello, hello. Army, hi, hi. Kesari Lal official, hello, hello. Sarim bhai, hello. Sumi Balian, hello, hello. The civil site, ER Arman, hello, hello. Aman Bharti, hello, bro, hello. Vapra, hello, bro, hello. Nanda Kishan KM, hello, Sarim, hello. Sumi Balian, nice name. Well, thank you. Atom Smasher, how is your chemistry? Haha. My chemistry, well, not that good, but I guess you already know that already. So no use even asking unless you're trying to make fun of me or of my chemistry. Like I'm at least doing physics and mathematics. Pretty sure it's better than what most people are doing with any of their subjects. Oh. Faxil, hello, hello. I guess there are no questions coming, like no actual questions. Nanda Kishan KM, have you heard of the time slit experiment? Well, yes. Now that is something really interesting. Well, the thing is that the double slit experiment is performed in space, but the time slit experiment is performed in time. You see, space and time are actually related to each other. Now that's relativity, even though when we consider slit experiments, so it's quantum mechanics. Now space and time are related to each other even in special relativity. And the fact that they're related to each other in special relativity is like time is the fourth dimension. And when we say space, we mean the other three dimensions. So here, special relativity and quantum mechanics can, of course, be unified into the quantum field theories. So special relativity and quantum mechanics, they don't contradict each other at that level as general and quantum mechanics. So the thing is that space and time and the properties of a space and time can be studied in the form of quantum mechanical laws as well. And of course, there can be, as it is consistent. Quantum mechanics is consistent with special relativity. So the fact that you consider the double slit experiment in space, that is in the three dimensions. So you have electrons, or you have maybe light passing through the two slits, and you consider their interference. So you consider the interference in space the very same way you could consider the interference of the electrons or maybe any other sort of wave or particle wave in time. And how is it possible? Well, you see that normally, considering just in the form of classical mechanics, non-quantum mechanically, there is interference in time that we all notice all the time, and it's beats. You see that interference in space, so that is when the waves are superimposed to each other. And but when you consider interference in time, you might think that oh, I haven't heard of such a concept or this and that, but you have heard it and you experience it a lot of time, and it's beats. And beats, like when you hear music, you hear beats to that, or when you have any two different sound waves coming, you consider yourself to be at different positions, and you, as you move across positions, you see that the frequencies differ. You don't have to move across position. When you stand at a single place, and you consider how the waves or the wave amplitudes vary in time as the two waves superimpose to each other. So that's beats, and that is interference in time. So the very same way we could understand it as quantum mechanically, the way interference occurs for electrons or any other kind of object or particle or quantum state in time. So it's something like beats. It's something like beats, not exactly beats, of course, because that is for the special case of sound waves, but something like beats that we are considering through passing through the two slits and interfering in time at the very same position. Yugam 65, in which class are you? Please tell. Uh, well, I'm currently ninth standard. Atom smasher, do you think that time can exist without entropy? Well, time existing without entropy, it's something like this, that time and space, I told you, are connected to each other. But the arrow of time, if we consider, it can be explained on three different levels, or not three different levels, but three different ways. It's the cosmological arrow of time, the psychological arrow of time, and the thermodynamic arrow of time. Now the thermodynamic arrow of time, that is, if we speak to the point here, is the arrow of time in which the entropy of a system increases. The arrow of time in which the entropy of a system increases. So whenever, as time passes, and it passes and in a single direction, in a single, along a single arrow, and the thermodynamic arrow of time passes along the arrow where the entropy will has to always increase. So to say that time can exist without entropy, I suppose it is the connection of the change in entropy with time that actually matters here. And regardless of whether entropy exists or not, or whether it always increases, there is always the cosmological and psychological arrow of time there. So it's not really sure whether the you see, concept of time can exist with or without entropy, but we know entropy is a useful concept when we consider the atomic or molecular levels, you see, at which the systems are changing thermodynamically. Khesari Lal official, can you understand me in short from from that, what is the special theory of relativity? Well, the special theory of relativity, it's something like, it's a theory that is based on two basic postulates. Einstein considered these two postulates, and he rested all of his special relativity on these postulates. And these are: the first postulate, that the laws of nature are all the same in every inertial frame of reference. And what we mean by inertial frame of reference is frames of reference in which we are not accelerating. That is, we are not changing our speeds, or if the frame of reference is itself moving, so it doesn't change direction. What is a frame of reference? Well, the place from where you're observing any given phenomenon. So, and the second postulate was the speed of light remains same, constant in all inertial frames of references. So Einstein based all of his special relativity on these two uh, principles, these two postulates actually, and the rest can be followed from here. The rest is just followed from these two postulates. You have Lorentz transformation, the equations which were discovered by Lorentz, and you have various other phenomenon that are actually going on over here, but all of it can be just followed from these two postulates. Vapra, will you give JE exam in future? Well, I'm not really sure. Tribhuvan Yadav, what is your plan to study in bachelor level? Physics and mathematics alongside chemistry. Now, chemistry, I have to take that, I suppose, so I'm not very much interested in chemistry. But physics and mathematics, yes, I am. Naman Mishra, bro, if I'm starting 11th physics, then is it compulsory to be familiar with differential equations? No, it is not. In fact, when you start 11th physics, so it's really not compulsory to be even familiar with calculus, because calculus is something that you learn in 11th and 12th mathematics. So there are chapters of calculus in 11th mathematics like limits, I assume, and there was derivatives, and 12th physics, 12th mathematics, that includes integral calculus, and it's 12th mathematics where you are actually introduced to differential equations. So the syllabus as formed by according to, you see, all as well. You don't have to be familiar with differential equations and not calculus either. Sayyid Nasir, is there any difference between gravitation and gravity, please? Well, uh, there is supposedly difference between gravitation and gravity, but it's not really that important to consider the difference between gravitation and gravity. In fact, the two terms are used interchangeably all the time, and it's not important. But yes, speaking of what is the difference, gravitation often refers to the universal force of attraction between all masses in this universe, between any two masses in this universe. Gravity often refers to the very same force, the gravitation only, but between an object and the planet or maybe the star that it is closest to, or it is standing or maybe flying on the surface of. So if you're on earth, well, then the gravity here refers to the gravitational attraction between you and the earth. If you're on moon, so it is gravitational attraction between you and the moon. So it's like that, but actually it's not really important to consider the difference between gravitation terms interchangeably. Pratik, do you know Ashish Arora sir? Well, of course, I do know Ashish Arora sir, and I'm so glad to inform. I'm so, you see, it's like I talked to Ashish Arora sir a few days ago. Like, Ashish Arora sir is one of my idols, and I talked to him a few days ago and received an invitation as well. So, might as well meet him. And he's one of my idols, actually. Vapra, please tell what is your dream? Well, I want to consider doing researches in physics. Arrow hit edits. What is the value of G at center of Earth? It's zero. Because you see that if you're at the center of Earth, all sides of Earth are pulling you, and they're pulling you equally. All sides of Earth, they pull you equally. Now, it's necessarily not exactly true. So it's like you have the equator and you have the poles. There is slight difference of not slight. There is a difference of 21 kilometers in the radius of the equator and the pole. So the Earth isn't really perfectly spherical. But any side that you consider, and the force of attraction from any side that you considered is as well cancelled out by the force of attraction from the other side. So when you're at the center of Earth, you find that you're not pulled overall pulled by anything because they're all cancelled to each other. Bhai, what is difference between lanthanide and antanides? Well, that's chemistry, I assume. Yes, Ari, official bro, do you know Walter Lowenzer? Now, of course, I do know Walter Lowenzer. I don't think anyone who is interested in physics doesn't know Walter Lowenzer. Okay. Beatty, what's your favorite equation of all time? My favorite equation of all time now, this is a difficult one. Like, I do have my favorite theories and stuff. Like, I really like conservation of energy and I like Needle's theorem. And I like the uncertainty principle. But to say just equation is really difficult. So I guess I'll go with Maxwell's equations. Yes, Maxwell's equations. How could I forget the my favorite formulations? Definitely one of my favorite formulations of all of physics. So Maxwell equations are. So that's four of them. Why are you giving J 2024? Well, I'm literally 9th standard. I can't. Are you saying E over B equals C? Is this right? Well, for an electromagnetic wave, yes, it is right. It is not right universally, because if you try to relate electric field in just any circumstance and magnetic field in any circumstance, you can't directly say the ratio is going to be the speed of light. But the electric field of an electromagnetic wave divided by its magnetic field is equal to its speed, and this is a result derived from the Maxwell equations only. uh, Albert Einstein, will you go MIT? Well, I don't specifically aim for MIT, I rather aim for Cambridge. Awaken gamer. Why space is dark? Because space is mostly dark interstellar space, to say, because there is lackness of light in it. Now, of course, you have light from all these stars coming and the sun. So when you're close enough to the sun, you definitely see light as from there. But when you look at these stars, so they're really far away and the intensity drops. I mean, the intensity drops really quickly. So that is the reason space is dark. Arrow hit edits. What is displacement current? Well, displacement current is basically it is something like this: the fourth Maxwell equation. So that is Ampere's law, and Ampere's law basically says that if you have any kind of loop, you have any kind of loop here, you can connect the magnetic field. And when I say magnetic field, I actually mean the line integral of magnetic field around this loop, and you can connect it to the current that passes through this loop. And what do I mean by current passes through this loop? Let's say you have any wire and you consider any imaginary loop. So let's call it the ampere loop. So you have a wire, you consider an imaginary ampere loop around it, and you basically take the line integral of the magnetic field around this ampere loop, and you say that this is basically equal to the permeability, that is mu naught, times the current passes through it. So that was stated by Ampere, that is Ampere's law. But Maxwell made a correction in this, and that correction is of displacement current. And he said that it is not that if you consider only this partial equation, that the line integral of magnetic field is mu naught times I. So this definitely leads to some failures in the case of, let's say, a capacitor. So in between capacitors, you cannot really see any such kind of charge flowing directly, and yet there has to be a line integral around the magnetic field. So what's happening? There has to be another kind of current. This he called the displacement current. And despite the uh, popular belief that displacement current doesn't carry any physical significance, it actually does, because displacement current is real. It's very real indeed, as real as the conduction current, to call the former. So what it is? Well, it is basically a way of transferring the charge you have by Maxwell equation. He added an extra term of displacement current in here. And how is this displacement current occurring? Well, it is occurring by the time rate of change of the electric flux that happens here. So whenever you are changing the electric flux, well, current is created there. What current? That is displacement current. So you see, in between the place of capacitors, there is charge showing up at different places, due to which you are seeing there is change occurring in between the plates of the electric flux. And that is how displacement current is created there, and charge flows there, and there is no induction current, conduction current, but there is displacement current. Pratik, I want to know whether you just know the theory of physics or you can solve problems of JEE Advanced, INPHU, and SCP, etc. Well, actually, to be truly studying physics is to be able to solve problems regarding the principles, corresponding to the principles. The thing is that you cannot know whether you really understand the topic without being able to solve problems of it, because then you're actually able to apply the theory to the respective problems. So to understand physics, of course, I believe problem solving is a necessity. So yes, I know the theories of physics, and I can also solve the problems. Like I've solved lots of problems even on YouTube, and you can find them. Like I solved the problems of JE Advanced many times, solved most of the problems of JE Advanced this year, not all of them, but I guess there were only 4 or 5 problems that I didn't solve this year. I solved all of them. I didn't try INPHO. I saw the NSCP and I thought it was solvable as for me. So yes, I can. But it's not that solving competition problems is all either. You might know theories of physics, but solving it within the time frame, I believe, is something that comes only with proper practice based on the very same competition itself. Linux user, रट के लिखना solving problems नहीं कहते. And for heaven's sake, I am literally answering live questions in front of you. And if you still believe that I don't know any of physics, so that is actually a defect in your brain, because I'm answering live questions right here. And if you consider that I'm cramming all of this stuff, I don't know all the stuff. So for the third time, I'm answering live questions. Now I'm doing it live. Can you recommend some prerequisites to study Griffith's quantum mechanics? I only studied Resnick, Halliday, Walker, Shahruz, Nomani. Some prerequisites. If you have studied Resnick, Halliday, Walker, then I think you're really you're okay with classical mechanics and at least the Newtonian formalism and thermodynamics. You have waves and electrodynamics and enough of modern physics as well. So I guess you could go with Griffiths, except the mathematical part. So you need a little more on the mathematical part. So it's like differential equations, not a lot of differential equations for Griffiths, not a lot of differential equations or so problem solving for differential equations for Griffiths. Though for higher advanced textbooks on quantum mechanics, well, yes, but little differential equations. And if you have already studied linear algebra, I think that definitely helps for whatever quantum mechanics you're learning. Linear algebra always helps. So that is what I would say. And rest you can work out through Griffiths just fine if you actually understood the things that you studied in Resnick, Halliday, Walker. And maybe try building up problem solving skills from more resources. I think that would help, because the problem levels in Walker are quite easy, as I think. Passion. Please explain what is friction. Is it van der Waals forces between two surfaces or the interclocking of two rough surfaces? Please explain. Well, friction is actually the interlocking of two rough surfaces. It's not really van der Waals forces between two rough surfaces. It's the interlocking. So you have rough surfaces and, well, yes, they interlock. And in that case, you have friction. But the very ironic thing I would say about this is that if you have the surfaces too smooth, well, then they stick to each other, yet higher friction. So contrary to the belief that smoothing the surfaces will reduce friction, in some cases it increases friction. So you can smoothen the surfaces, but you can smoothen them only to a certain extent, and to that extent only can you decrease friction. So it is actually the interlocking. And Lolite, by the way, you know what? You're better than Kautilya Pandit about that. But I suppose that he has also recently been studying physics. So I really don't know about general knowledge or all of that. And I'm pretty sure he's better than me in general knowledge or anything. I don't know about physics. Naman Mishra, how do you revise all those things which you have studied? Well, the thing is, I don't actually revise the things that I've studied, like not in a very classical manner that you have notes and you basically review your notes or you review the textbooks. I actually don't do it in that manner. And indeed, I do make notes oftentimes, but I have not once ever looked back at my notes. And the thing is that I basically solidify my understanding by problem solving at the instant. And even after problem solving, we of course forget things many times. We do, and everyone does. So where is the catch in this? Like, how can I basically retain all the concepts by mere problem solving at the instant and solidifying my understanding at the instant, and yet not forget later on? And that is the thing that I keep thinking about this stuff, and that is what actually matters. So I am using the laptop. Well, there are semiconductors and transistors being used inside this particular thing. Well, how does this particular thing, as I'm charging it right now, how does it charge? Well, there are electrons flowing and it charges the battery. So there are lots of things, the physics of transistors, that you can learn just by looking at the inner workings of your laptop or anything around you. So if you keep thinking and trying to understand the stuff around you, and that's what matters, trying to understand the stuff around you, you're not basically going to forget all of this stuff. And derived formulas, I'm not talking about fundamentals, but derived formulas, yes, I forget them oftentimes. But actually, those concepts that I've studied and held deep in mind, I think them and I try to understand the workings of the world around me. So that is how I actually am able to retain the concepts. Shahroz Nomani, I also have 3 volume Feynman lectures, which will be better for Griffiths or Feynman. If you say quantum mechanics, so take aside the other 2 volumes. So I'm assuming you have enough knowledge of the other parts of physics that are necessary prerequisites for quantum mechanics. But if you consider the 3rd volume of Feynman lectures, that is essential quantum mechanics, and Griffiths quantum mechanics, then I would say that understanding maybe a topic or a chapter or maybe the entire book of Griffiths and then going over to Feynman will definitely solidify your understanding a lot. So when you know how to calculate stuff, and then you know the mechanism, not the exact mechanism, that why they're doing this way, because no one knows, but at least the mechanism till at the level Feynman tells you will definitely solidify your understanding a lot. But again, it also comes down to individual preferences and understanding. So that this is how I do things. Aro hit edits. What do you think about Big Bang? I would like to say on this that I was watching a YouTube short of Sean Carroll, and he's a physicist, a great physicist, and he said that the Big Bang is not the beginning of the universe, rather, it's the end of our understanding. And I quite agree with that. Because Big Bang, you see, the way it considers that the universe is born out of a singularity. Now, singularity, that is infinities in physics, and they don't really make much sense. So, if you rather consider the uh, field version, what should I even call it? So, Big Bang as a studied using the rules of quantum mechanics, and yes, it has been done. You could look over Hawking's researches. So, the Big Bang can be understood even without the use of singularities. So, the universe could have begun without a singularity, and that I believe could be very true. But what was before the Big Bang, or what exactly happened at the moment of a Big Bang, is beyond our standing right now. So, we can't say much about that. What was before, well, according to our current level of understandings, what we can see is that the Big Bang is where we believe time began. So there is no sense in asking what was before the Big Bang, because there was no time before Big Bang. Abhay, can we split nucleus? Well, yes, nucleus has been split, so you can do it maybe under LHC or under any such atom smasher. Amin, Kepler law applicable for satellites or not? Well, the thing is that satellites if you consider any natural or artificial, they are very much like two planets what planets are to the sun. So they very much can be said, the Kepler's laws very much can be said about the orbits of satellites around planets. But the thing is that, well, yes, the orbits are elliptical, you know, they are elliptical. And you know that this particular time, in a particular period of time, the area that is swept by the satellites, well, yes, that is basically equal for all the same durations of time. So Kepler's laws very much are applicable for uh, satellites as well. Atom smash. If time is the fourth dimension and time, as some say, is an illusion, would you say that we do, you know, what that we do today affects the past? Do you know about the proofs of retro causality? Well, if anyone says that time is an illusion, I would say that is his personal opinions, and opinions don't hold in physics unless you're talking about quantum mechanical interpretations. So, to say time is an illusion, well, no, time is actually a dimension. Time is a dimension. So it's like, the if you say time is an illusion, you might as well say, and you have to say then, because it follows using the principles of logic, that space is an illusion as well. And if you say space is an illusion, well, you say you're living in an illusion. And well, that is the concept of this simulation hypothesis. And I don't really believe in simulation hypothesis. So here, time is really not an illusion unless you're considering something like simulation hypothesis. So that is on the basis of opinions. But we, in physics, we need observations for things. And there is no theory or physical model that says that time is an illusion. So, well, no. But can things in the future affect things in the past? Well, yes, that is possible. And it is not in the way you think, but it is quantum mechanically. So the past is actually not definite. It is just as definite as the future is. And you know, quantum mechanics says that that there is indeterminacy in the outcomes of measurements, and the fact that there are just probabilities and no exact happenings that are going on in quantum mechanics, it says the very same thing for the past as well. Abhay, what is Einstein theory of space? Well, based on the physical models as presented by Einstein, the general theory of relativity, to be very precise, we believe, according to Einstein's theories, that space-time is actually, the geometry of space-time is curved under the presence of matter in it. So here I would quote John Wheeler, and John Wheeler says that matter tells space how to curve, and space tells matter how to move. So it's like, under the presence of mass, the geometry of space time itself curves. And when that geometry curves, the other objects that are moving along, even if they were to initially follow straight line, well, they no longer follow straight line. Instead, they follow curved path. And why do they follow a curved path? It seems to us that something is pulling them, like light coming from a distant star. It passes right through the sun. The sun is such an heavy object that it curves the geometry of space around it. And when the light passes nearby sun, we might think that, why is the light getting deflected? Photons have no mass after all. Well, photons have no mass, so how is that affected by gravity of the sun? Well, the thing is that the sun isn't pulling the photons, or it isn't pulling the particles of light by Newton's law of gravitation. What the sun does instead is it curves the geometry of space around it and of time around it, due to which the light, which is actually still moving in a straight line, but the light moves in a straight line in a curved space. And the fact that it moves in a curved space in a straight line makes it seem like the light is actually curved, or the light is deflected off its path, but it's the space time which is actually curved right here. So and this is what Einstein explains as gravity. It is the curvature of space time in the presence of matter. So the You see, we can study physics, we can study cosmology and astrophysics on the basis of Einstein's general relativity. And that Einstein believes is the underlying principle of gravity. Babu Moshi, future doctor, please tell me how to focus on study for a long time and increase my IQ. Well, study what you like to study, I suppose. So try developing an interest in that. Try seeing the things you see from more like a perspective where you have to actually use them in future, or where you're interested in them. Just the things that you're interested in them, and you have to be interested to actually study something for a long time or increase your IQ. Well, on the part of increasing your IQ, much of IQ, I would say, is as well inherited if it explains anything. But again, Stephen Hawking says that people who boast about their IQs are losers. And I don't think either that IQ plays much a role. Swani Kumar, please explain YDSE. Well, I'm not sure what you mean by YDSE. Awakened gamer. Then why does it seem dark on moon? Uh, well, if you're asking me why once you stand on the moon, or once you are on the moon, why does space seem dark while on Earth it seems all bright and blue? Because moon has no atmosphere, so at night both the earth and the moon look the same, or at least the sky looks the same both from the earth and the moon. And why is that? Well, there is no sun in that, so of course it has to be dark in the day, at least if you consider. So on earth, what happens that as the light enters the atmosphere, it gets scattered around, and blue color is the one that gets scattered the most. And blue scatters the most, and that is why the sky appears blue. On the other hand, the moon has no atmosphere to scatter of the sun's light or sun rays, and that is why uh, even in day, considering that the sun appears there, you still see no sort of color in the sky except black, which is not really a color. Bhai, how many states do you know either than solid, liquid, and gas? Well, there's a plasma and there's Bose-Einstein condensate. Pretty sure if you study solid state physics, there have been more states discovered, but I am not really much into solid state physics, and I haven't learned much of solid state physics yet. But there's these five states. That is the three primary: solid, liquid, gas, and there's plasma and Bose-Einstein condensate. Hisari Lal official, bro, can you tell me what is Chandrasekhar limit? Chandrasekhar limit, it is basically the minimum mass of a star that is needed for the star to turn into a black hole, or might as well call it the maximum mass of a star that prevents it from becoming a black hole. So you can use the interchangeable definitions. What it basically says is that there is a certain mass limit. So you have a certain amount of mass, some number times the solar mass of our sun. And when a star of this much mass, it collapses under its gravity. And when that happens, when the fuel that the star uses to radiate off radiation, well, that ends up. And when that ends up, so what basically happens is that a star of this much amount of mass or higher mass, it collapses under its own gravity. And you see that there's Pauli exclusion principle, which often prevents it from collapsing even further. And it happens in the cases of white dwarfs and neutron stars. Pauli exclusion principle helps it to balance against gravity even after it has been ended up of all of its nuclear fusion inside it that radiates of radiation. So, but with mass higher than the certain amount of Chandrasekhar limit, Pauli exclusion principle cannot help, and it just collapses and collapses to a point where it turns into a singularity. And that is that this Kepler speed at the surface becomes so high that even light cannot possibly escape, and that is a black hole. Abhay, do you know the China's sun experiment? Well, yeah, I suppose in China they have achieved a temperature higher than the surface of the sun, right? Jaswani Kumar, young double slit experiment. A young double slit experiment performed by Thomas Young was originally an experiment to show that light is actually shows a wave behavior. So Newton and his contemporary physicists believed that light has particle nature, but Young performed this experiment and he showed that light shows interference, which is actually a, a wave behavior. So it's like light passing through two slits. You have a boundary over here, light shines over that, light passes through two slits. Well, if light showed particle nature on the screen behind this boundary where the slits are located at, just those 2 points or the points corresponding to those two slits should be where the light lands, but it doesn't happen to be the case. Instead, you find light interfering the same way as a web. So, not only at those 2 points, you will see across the screen, you will see fringes, dark and bright fringes of light. What does that mean? Well, light is an electromagnetic wave. The same thing can be done by electrons as well, and it shows that electrons as well show those interference patterns. So, quantum mechanical ideas that all these waves or particles, as of classically, show either particle or wave nature depending on the scale of their action. Mohsen Maxwell about accelerating electron. Well, when an electron accelerates, so what it basically does is it radiates out energy, and this energy is carried as well as certain momentum is carried. And how is it carried? Well, this energy, so you have an electron and as it oscillates or as it accelerates, what it basically does is it disturbs the electromagnetic field around it. And when I say that, and I told you that energy is radiated, energy comes out of the electron. Well, it is not something physical that comes out, but electron radiates energy, and it radiates energy such that the electromagnetic field is oscillating around it, and this electromagnetic field carries that energy. So something has to be there to carry the energy. It is carried by the electromagnetic field, so a disturbance in the electromagnetic field, and certainly an energy being transferred. Well, that is a wave. So that is an electromagnetic wave having the same speed as speed of light. So you have the light right here, that is an electromagnetic wave. So accelerating charges emit electromagnetic waves, which on a certain range of frequencies is nothing but light itself. Here, Awaken Gamer, what is Big Crunch? Well, it is basically the way that there has been theorized an end for the universe. So it's like the if the universe began with a big bang, it has to end somewhere, or maybe not. But the universe might end somewhere. So it goes on to expand and expand and expand, and then it begins contracting again, and then it contracts to a point again, and that is big crunch. So what we call it, Winkle NSC NCS, is Halliday Resnick best for JEE means at 11th syllabus from 12th class means in 1 year with this book preparation for JEE? Well, I wouldn't say it is very relevant for JEE mains or any. I wouldn't say it is really relevant for JEE. Self study in physics, interested in physics, well, yeah, it's pretty good book. The glass, please take my question. I'm not good in physics, but I really want to study. Please suggest me a strategy to study in 11. Also, please suggest me some theory books for self study. Thank you for motivating me in physics. Well, welcome. And regarding a strategy to study in 11 standards, so you must focus on the principles. So always try to focus on principles. That is what I would say, because there is no single trick, of course, that helps you study physics. That you know this trick, now you can solve physics problems or you can understand. But you must focus on the principles, and you must see that how you can basically understand that particular system or that section of nature that you have chosen. So how you can understand that section of nature, using this one principle. So you have the theory of gravitation. Two objects are attracting each other. So you're basically just using this principle alone, you're able to understand how an apple falls or how the moon orbits the earth. So it's fascinating indeed. Like it's so fascinating. You have one principle, you have one formula, you can figure out the motion of the planets. So isn't that really fascinating? So you must focus on these principles and then try to work out the mathematics or figure out the mathematical methods needed for these principles to work in some specific situations. And that said, of course, you need good mathematical methods and techniques as well. So you need good mathematical understanding as well. So try focusing on these principles and using them to solve problems, and try strengthening your concepts by solving problems. That is how you do physics. Some purely theoretical books. So, if you mean popular science books in any case, well, that would be A Brief History of Time and The Elegant Universe, Brian Greene, and The Grand Design, Stephen Hawking. Naman Mishra, how much maths you know till which class? Not on the basis of specific standards, rather on just how much I needed in physics. So it's like I certainly know calculus. So I know calculus and algebra. Well, of course, I do know algebra, trigonometry, coordinate geometry, and these are the basic mathematical techniques or mathematics that you learn earlier. So these are basic, and I guess anyone just knows about that much. Coming to next, I know linear algebra. I'm not really fluent at linear algebra or anything, but yeah, I know linear algebra, how it is used in quantum mechanics. And I know differential equations. Again, not fluent at differential equations, but yes, I can use differential equations as much as I have to use it in physics. So that's it. Vector calculus. Well, yes, I know vector calculus, and I have yet to learn tensors. So I'm planning on learning tensors now and group theory. Okay, so can you solve JEE advanced question? Please reply Soumya P. Well, I have already solved various JEE advanced questions on YouTube. You could check them. I can't claim to be able to solve all of them, and I often forget these derived formulas. So, but yeah, if I work on it just on the base, just specifically for JEE advanced, so I guess I can confidently say I can solve just most of the JEE advanced problems. But I don't study for that specifically. Saying on top of that, if I really have to say it, I can solve lots of JEE advanced problems. Winkle NCS Bro recommend books for JEE for physics and maths full study with proper grip on concept for JEE 2025 self study. Well, I would say for physics and maths. So in physics, you have H.C. Verma sir's concepts of physics. Now it is like concepts of physics is often used, but it doesn't really cover that many problems. So it doesn't have that many problems as would be needed for really solving competition level problems, or for actually getting a very proper understanding from a competition perspective. So I would say just use any well-known competition book for specifically aimed for J. Even though I say that competition books really don't teach you physics, or they are just presenting you with methods to solve specific problems. So try learning the concepts as well. Like HC Verma is good for that if you want to study the concepts at least at that basic level. And maybe competition books. I would rather say a good book like HC Verma that actually teaches you physics with problem sets. So that will really be good. Black body radiation, Mohsen. Well, black body radiation is something like this. Black body is actually a hypothetical object or a hypothetical body, and all the light that it supposedly radiates out, all the light that reflects over it or that is transmitted over it. Well, if it reflects all this light, then how is it basically possible that it is black at all? Well, it doesn't do so. It doesn't do so in the region or a spectrum of frequencies or wavelengths that human eyes can perceive. Rather, it's basically in infrared region maybe. So in that case, you can't see that, and you'll see the body is perfectly black, whereas it's not so black at all if you were able to see the infrared region. I mean, Fatima, would you prefer DC Pandey or HC Verma? So I said HC Verma would be basically good with any other problem solving books. So that might be DC Pandey. But competition books really don't teach you much physics, I say. So I would say HC Verma. Beast Slayer, what are your thoughts on the origin of the universe? So, the origin of the universe, as supposed by the Big Bang theory, so it's like it begins with a singularity, but we could as well do quantum mechanics into it, and we find that you don't really need a singularity to do that, and to consider the beginning of the universe as explained by physical models, and that's what I particularly believe. But that is not a very complete understanding either. So, general relativity is still a classical theory, it's a classical field theory of gravity. So, we need better theories like quantum gravity to truly understand what happened at the beginning of the universe. Daily math tricks for competitive exams. Do you think time is hypothetical concept or a dimension? Well, time, of course, I believe is a dimension, and anyone who knows or studies physics knows that time is a dimension. So it is one, as explained by relativity. Time is a dimension. Beast Slayer, thank you very much, little bro. Well, welcome anytime. Mohsen, how was Planck then able to explain the concept of quanta? Well, you see, there was this catastrophe, the UV catastrophe, and this certain problem that if what the Wien's displacement law and all these laws that were being found at that time before 1900s, if they were really true, everything in this universe, every object in this universe should actually radiate light. And as I told you about black body radiation, so it basically reflects all the light that falls upon it, and yet it does so in the infrared radiation, infrared spectrum. And if you have any object, it definitely radiates light in that case. And if it all radiates light and everything in the universe does, well, this universe should be filled of infrared radiation. And in that case, since everything that has radiates radiation or light, you consider that they have certain temperature and they also radiate energy with it. So that's thermal energy that can be converted as a form of it. So you basically find that everything in the universe should be so hot and we should die of skin cancer. So what is really happening? Well, Planck proposed the idea that even though they radiate, what basically happens is that the energy carried by any light or any electromagnetic wave or radiation does not come as in a continuous form but in discrete forms. And with that, he solved the problem of the UV catastrophe, that is the ultraviolet catastrophe. So even though I said it infrared radiation, the real trouble is actually of ultraviolet radiation. So when he says that, so not all objects can radiate this amount of energy or that amount of energy as of carried by packets. So it's carried by packets, certain packets of energy, certain factors as given by the Planck's constant, the original Planck's constant. That solves the UV catastrophe. Ayush Mishra, bro, please explain me what is actually a potential difference. Well, it is a difference of potential between 2 points. In the most simple manner, that is what I would say. But then, what is a potential? So, in under any case, I would say it is always better to learn what is a potential difference, or at least the physical significance, than what is a potential. And yet, if I have explained it that way, what is a potential? So you see that you can assign fields to every point in space for, let's say, an electromagnetic field. So you have electric charges and all this thing. You have electric charges, then that electric charges has a certain field in space. You have lots of them. So they all create their own fields, and the total field at any point is found by the superposition of fields, right? So the sum of all fields at each and every point. But if you were to carry out the very same things in scalar forms, which is often easier, so fields are vectors and they are really a pain to deal with. You can as well carry the things out in scalar form. So instead of fields and forces, you could work with maybe work and energies. So how do you do that? Well, if you instead of a field, you consider basically work that is happening or such and such things, you also need to consider certain thing that is a potential. And what is that? It is defined to be the amount of work that must be done on a unit charge to bring it from the infinity to a certain point, and that is the potential at that point. So the way you define field on a particular point, so a particular number that you're assigning with that point, and that governs what direction of force is exerted or magnitude of force is exerted on a charge. And I'm speaking it in the context of electric charges and electric fields, so might as well consider other sorts of fields and potentials. But as of electric forces and fields I'm speaking of, you might say that the way you have assigned a field to a particular point, you can also assign a potential to a particular point. What's that? Well, you say it by relating it to the work that must be done. What work must be done? Well, you want a charge, you take a unit charge and you carry that unit charge from where? From a very far away place where the field is essentially zero. And that is from infinity to say mathematically. And you bring it to one particular point and you do so, and you are trying to basically, you see, cancel out the repelling forces, so that it's a field, so it definitely pushes you away or pulls you towards, but you are carrying that charge. If the forces push you away, well, you need to push this thing and bring it to a point. If the forces pull you, well, then you need to exert a backward force, because you have to maintain a constant velocity, zero acceleration. Remember that you want to bring a charge from infinity to a point at constant velocity, zero acceleration. So depending on that, you choose the direction of force as well. So it is something that people often confuse it. If the charges are actually attracting you, you need to apply force in the opposite direction, because constant velocity matters, because then you can easily use Newton law and equate the two forces, your force and your work, and the electromagnetic field's force or work. And then you say that the work that you have done against the electromagnetic force to bring it from infinity to one point, and you divide this by the charge, or maybe say it was done on a unit charge, that is the potential at that point. And the difference between potential of 2 points, that is potential difference. And so that can be said that the potential difference between 2 points A and B is the work that must be done to bring a unit charge from one point A to the other point B. So potential difference, the work must be done on a unit charge to bring the charge from one point to other. That's the potential difference. Nathan S. Motivation Army, why intensity and gravitational acceleration is same? Well, gravitational uh, field intensity, if you say so, so it's basically defined to be that way. So gravitational field has been defined to be that way, and it happens to be equal to gravitational acceleration. But do not confuse, they are physically distinct quantities or terms. Soumya P, how did you learn quantum physics? By the way, how did you manage your time and how you able to understand these tough concepts? Um, Regarding learning quantum physics, lots of prerequisites, lots of mathematics, and then you only are able to do it if you really want to understand it, or you want to really go at it at a deep level conceptually. I mean, the maths of quantum mechanics, as they say, is not so difficult. The maths of quantum mechanics is not really difficult. I mean, it is linear algebra, some differential equations, but it's not so difficult if you compare it to maybe some other branches of physics only. So it's like general relativity. I haven't learned tensors yet, but I know that it's really difficult. So at least non-relativistic quantum mechanics, the mathematical part, I have already dealt with that kind of mathematics before, even before learning quantum mechanics. So the mathematics is not such a problem, but yeah, some integrals to carry out, they feel lot of work to do, but that's lengthy, not difficult. It's the conceptual treatment of the subject that's really difficult. So to actually understand things conceptually, like recently I shot a video about why the uncertainty principle, and that was the title of the video. So I told you that why the uncertainty principles are valid, why don't you aren't you able to measure these two quantities simultaneously, and I explained that pretty well, as in my opinion. But you see that it really took me lots of days to actually wrap my head around that concept, because if you ask anyone why can't you measure the position and momentum simultaneously, well, if they already have a proper knowledge of quantum mechanics, even if they have a knowledge of some knowledge of quantum mechanics, unlike I'm saying that, well, you don't ask someone who has only read popular physics books on the subject. So well, they say that the commutator of momentum and position operator, well, it is non-zero. So there is a certain non-zero commutator. To be speaking very precisely, it's iota h bar, the imaginary time number times the reduced Planck's constant, and this relation is called the canonical commutation relation. And the fact that this commutator is non-zero is the reason why the you have the Heisenberg's uncertainty principle. But that's very mathematical, and well, you can carry out this. It's some simple mathematics. You can figure out the commutator rather really easily. You can derive the generalized uncertainty principle really easily. It's really easy to derive the generalized uncertainty principle mathematically. But if you ask someone and this is how they reply, they don't really know the concept well. And I explained in that video what is the real mechanism behind this. That why is it that there are certain standard deviations and their products are always greater than or equal to h bar over 2. And you can watch that video and see my approach to this particular thing. And I didn't really read this thing somewhere that yes, this is really how uncertainty principle arises from physical perspective. Rather, I had to think hard and hard on that particular topic. And despite the fact that I knew that the canonical commutation relation, and yet I was not satisfied by that explanation. And thinking hard and hard, yes, I arrived on a conclusion that this is the mechanism behind it. This is why the uncertainty principle is valid. So conceptually, it's really a difficult topic. So I have to think a lot over that. How do I manage my time? Well, I'm only doing physics. I mean, I'm only doing physics, I'm only doing maths. So no problem with managing my time. How am I able to understand these tough concepts? Well, I explained you how. So you need to think a lot, devote a lot of time, and uh, invest a lot of brain cells into that. Daily math tricks for competitive exams. Do you think quantum theory can explain everything? Well, not even a matter of thinking, because it can't explain everything. It doesn't include gravity to it. Even if you consider quantum field theories, it doesn't include gravity. And there are still lots of flaws in quantum mechanics, I believe. I mean, I watched a video of Girardi who today only, and even he spoke of the flaws of quantum mechanics. Of course, I believe so too. There's the problem of renormalization. Feynman called it a hocus pocus trick. So, renormalization is just a mathematical trick to get rid of infinities in quantum field theories. It's nothing real. It doesn't explain physically realistic things or phenomena happening. So there are lots of flaws in quantum mechanics still, plus it doesn't explain gravity. I think I'll I think I'll stop the streaming at this point only, right? So, all right, so here's this question of, hey, bro, what is magnetic shielding? Well, magnetic shielding, you can basically protect these electromagnetic or any electromagnetic sensitive instruments from maybe external fields or magnetic effects by maybe closing it inside some particular kind of, you see, conductor, for instance. Because if you have a conductor or maybe a surface. You have some closed object that may be electrical, that may be even a conductor. But when you keep the closed, keep a particular, you see, charge inside a conductor, it all comes to the surface. And the fact that it all comes to the surface, there is no field inside. So you can place any electromagnetic sensitive instrument inside that particular conductor, and so, since it is electromagnetic sensitive, it is sensitive electromagnetically to say, so it won't have any effect, or any other charges or fields won't be having any sort of effects on this particular thing. Rambo, what is Doppler effect? Well, Doppler effects, it is basically how when you move towards a particular source of wave, so how the frequencies at which the wave arrives at you changes, or when the source of wave moves towards you, so how it changes. That is the Doppler effect. Can be done relativistically as well. To go in depth, it will involve equations, which I'm not doing right here. So in that case, uh, all right, all right. I'll consider this last question. Um, Nameen Fatima, last question. What is photoelectric effect? Well, photoelectric effect is how you can knock out electrons of a metal surface by shining light on that particular thing. So you shine light on a metal surface. So the light basically carries photons, and that is the bundles of energy, packets of energy. And each packet of energy is given to a particular electron. And since the energy contained by one packet is directly correlated with the frequency of the wave shined at the particular metal surface, higher frequency, higher energy. So if you shine a light of frequency high enough, so you can basically provide one photon to each electron inside the surface, the free electrons actually. And when one photon of energy is distributed to each electron, and if you basically have the number of photons, well, is number of photon electron emitted equals to number of photons incident? Not really, not really. So if you basically have any particular photon, and that gives energy to one electron right here, so that the electron might be emitted out of this and might go away from the material. So that is the photoelectric effect. And to answer that question, it is not equal, because you have things like work function. You have to get away from the material before it pulls you back. So, and since you have so many photons inside light, so the number of photons doesn't basically equal to number of electrons. Some photons are able to provide energy to some electrons that happens to collide with it. That is what is basically the mechanism behind it. And I'm stopping this stream right here. So it's basically 1 hour and about 10 minutes. That was all for today's stream of mine. And thanks to all viewers, and good night.